A conservative field is a special type of vector field where the work done to move an object from one point P to another point Q only depends on the initial position, so that's represented by the position vector to point P, and the final position being represented by the position vector to point Q. So for example, moving a mass placed in a gravitational field from point P to point Q over any path between these 2 points requires the same amount of work. So if we have a vector field defined in an open region in space, so we'll call this a region V. So recall, by an open region, we mean that every point in a region is the center of an open ball that lies entirely in the region. So in a conservative field, the line integral, being the dot product between the vector field and a displacement vector, along any path C from an initial point P to a final point Q, is the same over all paths taken between those 2 points. So that means that this integral is path independent, and the field F is a conservative field on the region V. So this comes from physics, where a conservative field means the conservation of energy holds in the region where that vector field is defined. So typical examples of a conservative field are the gravitational field. So given a planet of mass m, the gravitational field is minus the universal gravitational constant multiplied by m over the squared distance to a point in the gravitational field, and that's in the direction of r, being the unit radial vector that points towards that point. So in other words, if we place a mass in this gravitational field, then the force that mass will feel is the gravitational force, which is equal to the mass by the gravitational field at that point. And the electric field is another example of a conservative field. So due to a negative charge Q, the electric field is Coulomb's constant by the charge on the squared distance to a point in that electric field. And that's multiplied by the direction vector, which points to that point in the electric field. So this is a unit vector r hat. So therefore, if we place a charge at this point, being charge Q, then it will feel an electric force being equal to the charge by the electric field. So if this is a positive charge, it gets attracted to the negative charge. So it gets pulled in a direction towards the negative charge due to the electric force at that point. Suppose we have a differentiable real-valued function, and this function has a continuous gradient vector. So we have f being the gradient of our scalar function. And these are defined on a domain. So we have an open region in space, and we'll denote this V, and this region contains a curve that joins 2 points P and Q. So the curve looks something like this, being an arbitrary curve, and this smooth curve, or piecewise smooth curve, is parametrized using r of t, being a function of t in the I direction, and another function of t in the j direction, and another function of t in the k direction, where t is between a and b. So this gives the direction of parametrization. So in this case, given the vector field is the gradient of a scalar function, then the line integral, being the integral of the dot product of f and a displacement vector along the curve, only depends on the values of the scalar function at point Q and point P. So effectively, f is called the potential function of the gradient field f. So an example of a potential function is a gravitational potential being a scalar function whose gradient field is a gravitational field. Now we can show this is true by using the chain rule to evaluate the derivative of the scalar function with respect to the parameter t along the curve, where this curve joins 2 points in V. So using the chain rule, we take the partial of f with respect to x by dx dt plus the partial of f with respect to y by dy dt plus the partial of f with respect to z by dz dt. So we can see this expression is the dot product between a gradient of f and the velocity vector. And therefore, if we take the line integral of this dot product between a gradient of f and a velocity vector with respect to t along the curve, so we're integrating from t equals a at point P to t equals b at point Q. So using this relationship, we have the integral from t equals a to t equals b of the derivative of the scalar function with respect to t over t. So this evaluates to the function of g of t and h of t and L of t, being the functions that parameterize the curve, evaluated at t equals a and t equals b, and therefore we end up with f of g of b, h of b and L of b, which is the function evaluated at q, and minus f of g of a, h of a and L of a, which is the function evaluated at point P. So given f is the gradient of a scalar function, we can evaluate this line integral by evaluating the scalar function at q and the scalar function at P, being the two endpoints connected by the curve. And you may recognize that this is the vector calculus analog of the fundamental theorem of calculus. So we have the integral from a to b of the derivative of a function over x is equal to f of b minus f of a. Now let's make a bit of room here. So generally, given a vector field defined in 3D space, so that has a component of x, y and z in the I direction, plus another component of x, y and z in the j direction. Let's move this across, plus another component function of x, y and z in the k direction. And these components are continuous throughout an open connected region V in 3D space, as shown here. And by connected region, we mean that any 2 points in the region can be joined by a piecewise smooth curve that lies in the region. Then f is conservative if and only if it is a gradient field for a differentiable function f. So in other words, the line integral over a curve between 2 points in the region, being q and p, is path independent. So no matter the curve connecting these points, the integral will evaluate to the same value. Recall that for a conservative field in an open region, being region V, that f was the gradient of a scalar real-valued function that's differentiable, and we derived the fundamental theorem of calculus for line integrals. So we had the line integral of the dot product between a conservative field and a displacement vector over a curve C that connects 2 points in this region by a smooth curve. Only depends on the values of the scalar function at the endpoints. So we had f of q minus f of p. So therefore the line integral over any closed path in region V is equal to 0. So for example, evaluating the line integral over this curve, which we'll call C1, gives f of q minus f of p, and over another curve in region V, where these two curves form a closed loop. So here we have the line integral of f dot dr over curve 2, which will evaluate to f of p minus f of q. So adding these together, we get the integral over the entire closed loop, which we can see on our right hand side evaluates to 0. We can determine if a vector field f is conservative by the component test for conservative fields. So if f is equal to a component function of x, y, and z in the I direction, plus another function b of x, y, and z in the j direction, plus another component which is a function of x, y, and z in the k direction, and this vector field is defined on a connected and simply connected domain. So as we said, if the domain is connected, then we can connect 2 points using a curve that lies in a domain. And by simply connected, we mean that every loop in the domain can be contracted to a point without ever leaving the domain. So for example, if this region had a hole in it over here, and we contract this loop to a point, then the point lies outside the domain, and this is an example of a domain that's not simply connected. So if this is a vector field on a connected and simply connected domain, where the component functions have continuous first partial derivatives, then f is a conservative field if and only if the following relationships are satisfied. So the partial of the third component function with respect to y must be equal to the partial of the component function b with respect to z, and also the partial of a with respect to z must be equal to the partial of c with respect to x, and the partial of b with respect to x must be equal to the partial of a with respect to y. So you can see the pattern here. So the partials of c and b can be seen as c being the third component and b being the second component. So we take the partial of c with respect to the y component and the partial of b with respect to the z component. And similarly for the other partial derivatives. So we can prove these conditions for the case where f is a conservative field. So in that case, we have f is component a in the I direction, plus component b in the j direction, plus component c in the k direction, and f is the gradient of a scalar valued function if it's a conservative field. So we have the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction, plus the partial of f with respect to z in the k direction. So in other words, if we take the partial of c with respect to y, we get the partial with respect to y And c is the partial of f with respect to z, which gives the second partial of f with respect to y and z. And using Clairaut's theorem, or the mixed derivative theorem, we have the second partial of f with respect to z and y, which is the same as the partial with respect to z of the partial of f with respect to y. So we see the partial of f with respect to y is equal to b. So that's equal to the partial of b with respect to z. And you can prove the other relationships in a similar way. So once we show that f is a conservative field using this component test, then we can find the potential function by solving f is equal to the gradient of f. So effectively, we're equating the left and right hand sides of this equation. So we end up with the partial of f with respect to x is component A, and the partial of f with respect to y is component B, and the partial of f with respect to z is component C. So we find the potential function by integrating these three equations, and we'll see that in worked examples. Suppose we have an expression that's a differential form. So we have a function of x, y, and z dx plus another function of x, y, and z dy plus another function of x, y, z dz. So this differential form is exact on a domain in space, which we'll call V, if the differential form, which we'll write in shorthand notation as a dx plus b dy plus c dz, is equal to the partial of a function f with respect to x dx plus the partial of f with respect to y dy plus the partial of f with respect to z dz. And a differential form is equal to the total differential. So we can write this expression as the total differential of f. So f is a scalar function defined throughout V. So generally, it's often convenient to express work and flow integrals in the differential form. So we have our integral over a curve of a dx plus b dy plus c dz. So if this differential form is equal to the total differential of the scalar function f on the domain V, then f being equal to the component function a in the I direction plus b in the j direction plus c in the k direction is the gradient field of the scalar function f on V. And therefore this differential form is exact. So therefore the test for determining if a differential form is exact is the same as the component test that we showed for f being a conservative field. So on a connected and simply connected domain, being V in this case, this differential form is exact if and only if the following relationships between the partial derivatives are satisfied. So again, the partial of the component C with respect to y is equal to the partial of b with respect to z, and the partial of a with respect to z is equal to the partial of c with respect to x, and the partial of b with respect to x is equal to the partial of a with respect to y. So this component test for exactness is equivalent to testing if this vector field is conservative. Find the potential function for the gravitational field where g, m and m are constants. So what we do first is check if the field is conservative. And to do that, we'll use the component test. So if we take the partial of the third component with respect to y, that gives z multiplied by 2y multiplied by minus 3 on 2. So we're just applying the chain rule here. By x squared plus y squared plus z squared to the minus 5 on 2. So what we get is minus 3yz on x squared plus y squared plus z squared to the 5 on 2. And if we take the partial of the second component with respect to z, we get y multiplied by 2z by minus 3 on 2 by x squared plus y squared plus z squared to the minus 5 on 2. So again, we get minus 3yz on x squared plus y squared plus z squared to the 5 on 2. So we see that these partial derivatives are equal. And similarly, you can check the partial of the first component with respect to z is equal to the partial of the third component with respect to x, and the partial of the second component with respect to x is equal to the partial of the first component with respect to y. So I'll leave it for you to check the second condition and the third condition, and you'll verify they're satisfied. And note that here, we ignored the constants for a shortcut because they'll appear in every expression. Now let's make a bit of room. So given the gravitational field is conservative, then the gravitational field is the gradient of a scalar function, being the potential function. So if we equate f with the gradient of f, we get the partial of f with respect to x is equal to minus g by m by x on x squared plus y squared plus z squared to the 3 on 2. So we can write this as the expression to the minus 3 on 2. Now separating the variables and integrating both sides, we can integrate the expression on the right using u substitution. So we have u is x squared plus y squared plus z squared. So du is 2x dx. So we can write the integral as minus g by m on 2, and we integrate u to the minus 3 on 2 over u. So what we get is minus g by m on 2 by u to the minus a half on minus a half. So therefore the negatives cancel and the 2's cancel. So we're left with this expression. So therefore we get f of x, y and z is equal to g by m over x squared plus y squared plus z squared to the half, plus a constant of integration. So in this case, our constant of integration will be a function of y and z. So noting, if you take the partial of f with respect to x, you obtain the first component of the vector field, and g drops out. Now let's make a bit of room here. So equating the second component of f with the second component of the gradient of f, we get the partial of f with respect to y is equal to minus g by m by y on x squared plus y squared plus z squared to the 3 on 2. And now if we take the partial of f with respect to y, we get minus a half by 2y, which is y. So that gives minus g by m by y over x squared plus y squared plus z squared to the 3 on 2 plus the partial of g with respect to y. So if we equate these two expressions, we see that the partial of g with respect to y is equal to 0. So therefore g is constant with respect to y, and this constant of integration is only a function of z. And similarly, if we equate the third components, we have the partial of f with respect to z is equal to the third component of the vector field. So we get this expression. And then taking the partial of f with respect to z, we instead get the following expression. So we get a z here plus a total derivative of h with respect to z. And again, if we equate these two expressions, we get dh dz is equal to 0. So therefore h is not a function of z, and is thereby a constant. And because we're looking for a potential function, we can just ignore the constant, because that represents an infinite number of possible potential functions. Find a potential function and evaluate the integral. So here we have the integral of a differential, and we use the component test to check if it's exact, and if that's true, that tells us the following vector field with component A in the I direction plus the component B in the J direction plus the component C in the K direction is conservative. So first we'll take the partial of C with respect to y, so that gives 2z on y, and compare that to the partial of B with respect to z, which is also 2z on y. So these partials are equal. And then we take the partial of A with respect to z, which is 0, and compare that with the partial of C with respect to x, which is also 0. So that's also true. And then we take the partial of B with respect to x, which is 0, and compare that with the partial of A with respect to y, which is also 0. So therefore, the differential form passes the test for exactness, and therefore, assuming y is greater than 0, so the domain of f is simply connected, we conclude f is conservative by the component test. And now to find the potential function, we'll just make a bit of room here. We have f is equal to the gradient of a scalar function, being the potential function, since we showed f is conservative. And now we compare the first components. So we take the partial of f with respect to x is equal to 3x squared. So separating the variables and integrating both sides, we get f of x, y, and z is equal to 3x cubed on 3 plus a constant of integration which depends on y and z. So if we take the partial of f with respect to x, the function g drops out, and we get 3x squared. And now equating the second components, we get the partial of f with respect to y is equal to z squared on y, and taking the partial of f with respect to y, we get the partial of g with respect to y. So equating these two expressions, the partial of g with respect to y is equal to z squared on y. And separating the variables and integrating both sides, we get g of y and z is equal to z squared by the natural log of y. And our constant of integration, being our function h, is a function of z. And now let's make a bit of room and substitute for g into our function. So we have z squared by the natural log of y plus h of z. And now we equate the third components of this equation. So we have the partial of f with respect to z is equal to 2z by the natural log of y. And taking the partial of this function with respect to z, we get 2z by the natural log of y plus the derivative of h with respect to z. So if we equate these two equations, we get dh dz is equal to 0. And therefore h does not depend on z, so it's a constant. So we can take a particular potential function by ignoring the constant of integration. And now we can evaluate this integral by evaluating f at the endpoints. So we have f of 1, 2, and 3 minus f of 1, 1, and 1. So as we can see, f of 1, 2, and 3 is equal to 1 plus 9 by the natural log of 2. And f of 1, 1, and 1 is equal to 1 plus 1 by the natural log of 1, which is 0. So the integral evaluates to 9 by the natural log of 2. Show that the following field is not conservative. So using the component test, we take the partial of the third term with respect to y, which equals 0, and take the partial of the second term with respect to z, which is also equal to 0. So this condition is satisfied. And the next condition is the partial of a with respect to z, which is also 0, and the partial of c with respect to x is also 0. So this condition is also satisfied. And now we take the partial of b with respect to x. So using the quotient rule, we have low d high, which is 1, minus high d low with respect to x, which is 2x. And that's divided by low squared, which is x squared plus y squared squared. So in the numerator, we have x squared minus 2x squared, which is minus x squared plus y squared. And then we take the partial of a with respect to y. So we have low being x squared plus y squared, d high, which is minus 1, minus high being minus minus y, by d low with respect to y. And that's divided by low squared, being x squared plus y squared, all squared. So we have minus x squared minus y squared plus 2y squared, which is minus x squared plus y squared. So these derivatives are also equal, and therefore the field appears to be conservative by the component test. But we observe in the denominator that x squared plus y squared cannot be 0. So therefore the field is not defined at the origin. And therefore, the domain of f is not simply connected. Because if we collapse a loop to a point at the origin, then the point is going to lie outside the domain of f. So the next check we make is that the line integral around a closed loop is equal to 0. So the integral of f dot dr must be equal to 0 around a closed loop for a conservative field. And the loop that we'll choose is a circle of radius 1. So that's parametrized by cosine t in the I direction and sine t in the j direction from t equals 0 to 2 pi. And we can write f in terms of t. So we have y is equal to sine t on cosine squared t plus sine squared t, which is 1 in the I direction, plus x, which is cosine t, on x squared plus y squared, which by the trig identity is 1 in the j direction, and we have a 0 component in the k direction, noting the circle's parametrized from t equals 0 to 2 pi. And then taking the derivative of r with respect to t gives us dr dt, which is minus sine t in the I direction plus cosine t in the j direction. And then doing a change of variables, we have the integral of f dot dr dt over t from t equals 0 to 2 pi. So f dot dr dt is sine squared t plus cosine squared t, which is 1, and therefore the integral of 1 over t from t equals 0 to 2 pi is 2 pi. So therefore the line integral over a closed loop does not evaluate to 0, and therefore f is not a conservative field over its general domain, because it's not a simply connected domain.